already might guess what we can now do. We have this map that gives us a map from vectors, like in R2, just ordinary vectors, into tangent vectors at the surface at a given point. And what we can do then, if the points match, like the p and the phi of x, y, if they match up, what we then can do is we can compose and go along like the alpha here. To get like something that maps vectors of R2 into linear maps. So what we do is we define alpha phi. It's the one form on here. We define this one form by saying that at a given point, it's the same thing as tx equals to 5, and then we compose this map. With the correct alpha. So maybe just like could provide this up. What this means is we plug in a vector. What we do is we first map that vector for phi to get another vector. So if you want to think of this, what we do is we have a vector here. Instead of the colors. So let's say we have some vector here. What we do is we push forward the vector. We consider the map that sends this tangent vector in R2 to a tangent vector at the surface. So that's this expression over here. And then we get a tangent vector at the surface, and then what we do is we just plug it into alpha, and for that we have to match points. So we plug it into alpha. That makes sense. And then what we get is like a map that assigns to tangent vectors on the open subset a number in a linear way that we can check, because this one was a linear map and alpha was a linear map. So in particular, this one is a linear map. So we indeed get it one form. This one is one form E, and it's called the chart representation. So we now got like a one form which is living on an open subset. As we discussed now quite some time, usually it's easier to think of these one forms in terms of the coefficients, which are calculated by plugging in dx and dy. So let's calculate the coefficients of d phi. Coefficients of alpha phi. So what we have to do is we give a point dx and y, and we plug in the vector field, say like dx, and then we have to do it the same thing with dy. So let's go to this last line and just use the definition. So what it is we evaluate alpha on dx, dy, and then we calculate dxy phi you can already think about what was this. So that, if you remember that, I think not last time or even like the time before that, 2 weeks ago, we talked about that this linearization of this map is essentially given by the Jacobian. And now if you plug the x in, that just singles you out one column of that Jacobian, or one row, depending on your cube point. So what we end up with is that this part here is just a partial derivative of phi in the x direction, evaluated at dx d1. So that's the coefficient. It's just to take the partial derivative of phi that gives you a certain vector, and then you plug this one in. So that's an important formula already that is quite handy in like applications. Whenever I ask you to calculate the chart representation of that one form, what you do is you just take the Jacobian of the chart, calculate, like take one of these columns or as a vector, and then plug this one into alpha, and then you get a number. So for every x and y. But if you remember from last time, we have seen these kind of expressions also quite often. So let's think about it a little bit more and reformulate it a little bit. So last time, we defined certain vector fields of phi, which was defined as a very similar way that we took dx, but then took the inverse image of phi. So that's a vector field, at least on the open subset of S. This gives you a tangent vector on S. So it's a vector field on that chart, which points in x direction. It's a vector field. And once we have a vector field, we know that we can plug that vector field into our one form that when we talked about, right? So we get alpha paired with that one form is a function on S, or to be precise on the chart. And last time we talked about once we have a function which is living on the surface, then we can also just like take it back with the chart to get like the chart representation of that function. So let's calculate this one. Chart. This function, which was just taking like the pre-compose it with the file. So what we have is that we have phi x phi. So that's it's a function, and then we want like to pre-compose that with phi of x and y to get a function of x and y. So let's calculate this in more detail. So this is we have this function evaluated at the point, so we get alpha phi of x dx, and then we have to evaluate the vector field as well at that point. So it's dx of phi evaluated at the point phi of x and y. So now we use use the definition of p phi of this vector field. So we use the definition now that dx in the phi up there was given by taking the partial derivative of phi in x direction and then phi inverse. So this phi inverse, with the phi inverse, kills this phi over here. So what we get in the end is that alpha dx phi, chart representation of this, equals to alpha dx phi, and then partial derivative of x at x and y. And now you look at the very first formula that I have upstairs, which is having exactly the same terms as what we just calculated. So what we get here is the chart representation of alpha on x. So that might look like a bit tautological, but like please be careful with like where the phi's are. So on this side here, we have alpha. It's like something that lives on S, and then we take a chart representation, which is something that lives on an open subset of E. So this one was this one is like on D, and this one is something that is on D. While this one over here, it's essentially the green part. That's this vector over here. With the, let me say, like B is in the x direction. So that one is actually a on S. So what we do is now we relate something that lives on S, like an alpha, and calculate the coefficients in that way, that we say like this one, the coefficients of the chart representation. So that's really like a way to get back and forth. So either you can say, if you have to calculate things like say in your homeworks, where you have to calculate this kind of expression, what you can do is like either you take this definition here, where you say, okay, I take the Jacobian and then plug it in alpha and get like a certain number. Or alternatively, what you can do is like you say, I want to calculate this, and what I can do is here, I calculate these vector fields, which are the vector fields on S, and then plug these one in S. And then I have to decompose the phi to get like, again, a number. And this calculation was showing you that both numbers actually coincide. Summary of this discussion is that the components of the chart representation alpha phi the chart representations of the functions alpha and here insert dx phi and so that gives you two ways to calculate the chart representation of a one form. Yeah, and like connects that. So in some way, like this picture is like that either we can consider like the vector fields and we can consider them like as like a vector field and up here, and pair them with alpha to get a function. Or I can do that one here where I have like a chart representation of that vector field. I plug that in a chart representation of alpha to get a function. And what this calculation is showing you is that like these two things coincide under this map phi. Two functions where we say like, okay, alpha paired with the vector field in green gives us a certain function on S, and here we plug in the chart representation of V in alpha to get a function on D, and then if I compose this function with phi, I get this function. So essentially that says that like it doesn't matter where I pair vector fields and differential forms. Either I can pair them on S or I can pair them in the chart representation, and it doesn't matter if I be a bit careful with like that they're functions of the same alpha. Okay, I think that was like already quite a bit of material, so let's go in a break. And then after the break, we'll talk a bit more about integration of one forms along curves. So continue, 20. In some ways, if you think of that in coordinates, then automatically that gives you this natural. So the thing is that, like here on the surface, it's completely independent. Like here you have like you don't need any charts to talk about changing vectors. But the problem is that usually if you want to think of that as in terms of and in order to do that, you need like to choose certain types of bases. Like the basis vector, you don't have canonical choice. So that's like the point is that like we want to have like certain vectors which we say is canonical in some way. So the only way that we can get them is by using a chart and saying, okay, in that chart we have canonical coordinates in x and y direction, y direction, order. And then we say like, okay, once we have that, we can consider them as like giving us this direction on the chart. So, okay, there is a relationship there. I think it's the same definition of the Leibniz rule. It's essentially a. The relationship that we have here is that like also of P. What we do is we that's the relationship between how you think of actually like a vector.
This definition we already at this time we already choose the trunk as but this definition we never choose
we call it like P times size because of C was like a curve. So this one is also a chart. So what we called was we have like a curve in the S line, which was smooth, and then we just take like the
but how to define this one? We only use these to define the address space. Integrate address space. But how to represent this one like this?
This one was represented by the curve from X and Y.
Yeah,
like
we already use X and Y.
So in order to find this guy, we need like the chart. But like the tangent vector in itself is completely independent. So it's really like here you can talk about like tangent vector independence, but these are just like just like the elements of an abstract tangent space. But like, what we would like to do usually is to represent two numbers. In order to that, we need like choose a chart. So it's really like this representation of a tangent vector in terms of two numbers that you can and for that you not like this would Okay, let's continue. So what I would like to talk now about is like the integration of a one form along a curve. So that will be the topic for the next few minutes, is integration. So we have alpha is a one form on the surface. And suppose that C is, let's say, defined on E to B is a smooth curve. So in particular, for every t, we can take the tangent vector, like the first derivative of c of t. So we can take the derivative in t direction. So this one gives us, by definition, an element of the tangent space of S. So you have a curve, you just take like the first, the speed of the curve. So that gives us a tangent vector at the curve, at the surface of the curve. And we have a one form. So what we can do is we can in particular plug in this tangent vector into the one form. And then of course the points need to match, so the one form needs to be evaluated at the correct point. So that gives us a number. So all of that is just like a number. So we get, for every t, we get a number. So what we can do in particular, we can just integrate all of these numbers over t. So in some way you measure, you can think of this term here, it's like the measurement of the tangent vector. So you measure some property of the tangent vector with this one form alpha. And then you get a number for every instant time t, and then you just integrate all of that. And by definition, we write this integral as the integral along the curve of the one form. So that's the definition. That's the integral of alpha along C. So that's the definition of the integral. So if you have a one form and a curve, you just plug in the tangent vectors along that curve into alpha, and then you get like a certain number and you integrate these ones up. One example. Suppose that we just look at like S to be the plane, and say we have Y as some vector field. Then define a one form alpha by saying we have alpha at some point p that eats a tangent vector, and what we do is we just take the vector field evaluated at the point p to give us some vector, and then we take the dot product of v, and that clearly is like a linear map for every p. This side is fixed, and then it's a linear map in V. So this one is really a one form defined by the vector field. And then suppose that C is a curve in R2, in our surface. Then the integral C of that alpha that we just defined. Let's have a look what this is. So we go back to the definition and just write alpha CT evaluated on C dot of T over dt. So now we use the definition of alpha to write this as the integral over just the inner product of y at a certain point times the curve in itself. And you might have like seen already expressions like that in some curves. So this one is the line integral of y along the curve. So the picture is that, say that is R2. Here we have a certain curve in there, and we are given a certain vector field that fills out R2. And what you do is you take the inner product of that tangent vector with this vector that starts at that point. It would be y c of t. That point is c of t. So you take, at every point, you take the inner product of the speed and the y. You get like something that measures how much the curve points in the y direction. So that value is of course the highest if like the curve goes directly in the direction of y, and it's like 0 if like the point if they're perpendicular. So that value, the inner product here, that measures how much the curve goes in the y direction, and then you just like sum all of these contributions along the curve. And that value is called like the line integral. So maybe you have seen that already. So in that way, we get a reinterpretation of something that you might have seen already. So the line integral, you can write this one as an integral over a certain one form along the curve. And it's actually a little bit more like natural to actually think of that in terms of this one form instead of really thinking that as a pairing with the vector field most of the times. So that's one example. So we have seen already that we get like a canonical one form, or like to every function we can associate a one form which we call df. So let's see what happens if you have like this one form and we integrate along a curve. F function and C is smooth curve. Then we can calculate the integral of the curve along the one form df. So that integral now makes sense because df is a one form on S and we have a curve, so we can like consider this function. And that gives us a number, and the proposition says that this is nothing else than we have C and we evaluate f at the endpoint of the function of the curve, and we take the difference with the value of f at the starting point. And you might have seen already an expression like this, and that's the fundamental theorem of calculus. So this proposition is also usually called the fundamental theorem. It's in a way that you might have not seen it. So let's see if the proof maybe, or maybe before we say something more, in particular, if C is a closed curve, so that means that C of A equals C of B. In that case, the right-hand side is always 0, because then this point and this point are the same. So that means in particular, the integral over every closed curve of this one from df is just 0. Okay, so let's have a look at the proof of this statement. So what we need to do at some point is we need to calculate alpha with the pairing of the tangent vector, and alpha in this case is just df. So let's calculate what this is. So we have to calculate df the one form. I have to give you a point, and then I plug in the tangent vector. So that will be the integrand. So let's go back to the definition of this one form df. So this is the same as taking the directional derivative of the curve at the point t of t in the direction c dot of t. So now you remember that like the tangent the directional derivative was given by that you choose some certain curve that represent this tangent vector, and you flow along that curve, and then you take d of dt. So in this particular case, we have like the curve already, because this one is the tangent derivative of the curve. So this in particular is nothing else than dt at the point certain t of the curve c of t plugged into it. So that's just the definition of the directional derivative. Okay, so that's the integrand. So now let's look at the whole equation. So what we get is that this one is a of b over df c of t c dot of t dt. So that's the definition of the integral. So now we use this calculation that we had to write this as a of b d of dt of f c of t dt. But this expression, you know, like this one is now the just classical fundamental theorem of calculus. That once you have d dt of a certain expression, then it's really just like the evaluation of that expression at the endpoints. So what we get is that it's this function evaluated on the endpoints, and that gives you exactly the statement of the proposition. So it's again something that that reminds you very much of like the like your calculus days. It's like but now we rephrase that in terms of functions and stuff on the surface. So it's actually quite remarkable if you think about what we do. We have some arbitrary surface. It's like we have an arbitrary surface that is nice and curved, and we have a function on that which gives you certain contour level sets. So that's like contour level sets of f. What you now do is like you have some arbitrary curve that goes like maybe something like that. And what you do now is in this integral, you calculate the curve and you at each point you kind of look at like how much is the tangent of that curve like hitting how many steps, so to speak, is it like doing up the mountain or so. So this one is like this contribution, this one over here, gives you this contribution of df at the point c of t, c of dot. It's like you think of f as like the measurement in terms of planes of the contour lines, and then this one is like saying, okay, how many lines do I hit like infinitesimally? And then you do that like along the whole curve to get some numbers depending on the t, and then you sum all of them up in terms of the integral. And what you get is a certain number, and what it is just the difference in height. So it's quite remarkable if you think of that in terms of like this. Like if I would have given you this question before, you would have maybe like struggled to find like this like statement. But it's like really just a very direct consequence of the fundamental theorem of calculus for this one-dimensional integral. So it's that's the surprising content of this theorem. So what happens is that sometimes you want to know what happens if you reparameterize your curve. So we had like at the beginning of the curve of the semester, we talked about curves, and like the first element that we did was, okay, we can always reparameterize our curve to have unit speed, for example. That was like if the curve is regular. So so it's often helpful to know what happens if you reparameterize. So let's say we have a one form on S and a smooth curve. And then we have, let's say, psi, which is a map from A prime from some different interval to the integral. And it's a smooth function such that the derivative at every point is not zero for all points in the interval. So we have such a map with non-vanishing derivative, and then the proposition is seeing that two things can happen. Like first of all, we take the integral now along this curve that we get from taking phi to be just like recomposing the phi to get a different curve. So this one is another curve, and we take the integral along this curve, and then two things can happen. Either we get the same result or we get minus the same result. And that depends on the sign of this derivative. So because it's non-zero, it's either positive or it's either negative. So we get a plus sign here if the derivative is positive, and then we get a minus sign if the derivative is zero. So this minus sign just says, like, essentially, for example, that if you go like with the curve from, like, if that's your original curve that goes in along this direction and you integrate along a one form, then if you turn around like and go in this direction, then you get like minus this the result. So it's like if you change the orientation of the curve, which is like essentially saying that you have a derivative that is smaller than zero, that changes to the orientation that you walk around, then you get minus the same result, and otherwise it's invariant under this reparametrization. So it's the statement that like says that whatever kind of parametrization you choose of the curve, it's essentially the same if the parametrization is like positive. So I don't want to give you the proof, but like it's essentially you do the same kind of trick as what we have done over there, is where you just essentially write down the definition of the left-hand side, then use some theorem that you know from your calculus class, probably something with substitution, and once you do that, you get like a certain expression, and then you calculate this expression in terms of the integral again. So it's a small little nice homework that you can do. Okay. So that was like quite a lot of abstract mathematics. So I would like to give you some idea of where these kind of integrals show up. And one of them is, of course, in physics. So what you can think of is that in physics, what you usually have is that this one form that you look at, that alpha here, is giving you kind of like the force field. So like, for example, you have like a certain gravitation that like pulls this bottle like down. That's why it's falling. So you have like certain a field of force lines that says like how much you go down in a certain direction. And you can think of that as very similar to this example that we had before, where you can think of that as a certain vector field. Or, as what is actually a bit more convenient, is to really think of that as terms of having that really as a one form. So this one form really kind of, you can think of that as a certain pulling of like, or a certain gravitation or a certain force field. So in physics, the one form